Hello friends, this is Anpichan. Welcome to my mathematics class. Let's move into today's topic. Today's topic is permutation. Main topic is permutations, and in permutations we will discuss one of the very important theorems. Before starting the permutations, we need fundamental principles of counting. So that's why I have here written the statement of fundamental principles of counting. We will know about the fundamental principles of accounting. What is the fundamental principles of counting? You can say if one operation can be performed independently in M1 ways, here M1 ways, in M1 different ways, and if second operation can be performed in M2 different ways independently, and third operation independently can be performed in M3 ways, and so on. Okay, we can have n operations, then the total number of ways in which all the operations here, all the operations can be performed in stated order is m1 times m2 times m3 and so on times and so on, right? This is your fundamental principles of counting. Fundamental principles of counting sometimes is also called basic principles of counting. Okay, so it doesn't matter, both are all the same thing, both are same thing. And one more principle we have here, I've written addition principle. If two events, let's suppose they are independent, right? They occur independently in exactly m1 ways and m2 ways, respectively, then either of the your events can be performed in m1 plus m2 ways, right? And then we add, okay, m1 plus m2 ways. That's why we say addition principle. Now I'll explain, okay, I'll use, okay, fundamental principle counting to find out the number of arrangements, to find out the number of ways, to find out the number of choices. Okay, let's see here. Now I think clear the statement. Okay, now you understood what is the fundamental principle of counting. Now I'll explain with example. I'll explain example, very good example. See, uh, one example. Let's suppose this is a school. This is a school, and 1, 2. Okay. Here 1 and 2. Number 1, number 2. Entrance gates. And number 1, number 2, and number 3 exit gates. Let's suppose we have in a school 2 entrance gates and 3 exit gates, right? Okay, now I'm going to make one question. In how many ways, a student can enter in the school, enter into the school and come out from the school and come out? Okay, in how many ways a student can enter into the school and come out from the school? Okay, let's see in how many ways. Clear? The question is in how many ways the student can enter inside the school and then come out from the school. See, here, to enter inside the school, how many gates are there? 2 gates. So here a student can choose any one of them, right? Either student can go from here or student can go from here. Okay, then student will have 2 choices. So student can perform here this activity in 2 ways. So M1 is here, you can say 2 ways, 2. M1 is 2 way. We can say, okay, a student can enter, okay, can enter into the school in 2 ways. We can say, okay, can enter into the school in 2 ways, okay. M1 is your 2, right? And then come out, okay, the student come out from the school in how many ways? There are 3 gates, 3 exit gates. The student can come out from either this or this or this. A student can choose any one of 3. All right, any one of 3. So and M2, okay. Now how many ways, okay, he can come out? In 3 ways, because he has 3 choices. 1, 2, 3. Anyone he can use, okay. So M2 is, okay, 3 choices. Yes, according to the fundamental principle of counting, if M1, if one operation independently can be performed in M1 ways, so M1 means, okay, this operation can be performed in 2 ways, and the second operation independently can be performed in M2 ways, so M2 is your 3 ways, and then total number of operations, right, total number of operations in which all total number of ways in which all operation can be performed is in stated order is, what is your M1 times M2. So what will be the total number of ways, okay. So here M1 we will use, okay, basic principle of counting. According to the basic principle of counting, formula is M1 times M2. We can multiply, right? If you want to find out the number of ways, in total number of ways in which student can enter inside the school and come out from the school, okay, so then, okay, your total number of ways will be M1 times M2 means 2 times 3 is equal to 6, okay. The student, okay, student can perform, okay, in 6 ways, okay. Student can go inside and come out from the school in 6 ways. Okay, so simple. This is called the your fundamental principle of counting. Okay, so you can see, you can check, okay, by counting also. If student enters from here 1, 2, 3 ways, right? And if he enters from here, he can 1, 2, 3. He can entering from this gate and coming out from this 1 and this and using this and this and using this 3 ways. And from 1 also 3. 3 plus 3, 6. So total, okay, total is 6. And by using fundamental principle of counting, we got 6. Okay, right? Now I think you are clear. Okay, now let me take one more example. Okay. To make it clear, fundamental principle of counting. Okay, next, okay. Let's make 3-digit number. 3-digit number from 1, 2, 3, 4, 5, okay. Let's make, okay, 3-digit number. We have to make 3-digit number from these digits, okay, 1, 2, 3, 4, 5, without repetition. Repetition is not allowed here. Without repeating any digit, we want to make the 3-digit number, right? 3-digit number we want to make. All right, 3-digit number. So let's make the box, okay, 3-digit number. And all right, let's suppose this is a unit place, this is a tens place, this one is your hundred place. There are how many digits? There are 1, 2, 3, 4, 5. So okay, now let's start to fill up the unit place. If you want to place the unit place, if we want to fill up the unit place, so any one digit you can take, okay, right? Any one, okay, any one, okay. You can, I'm writing here, any one of 5 digits. Any one of, okay, 5 digits. For unit place, you have 5 choices. So how many ways? 5 ways, okay. We can fill up in 5 ways. Okay, so unit place in the M1 is, okay, 5 ways. Independently can be filled up in 5 ways. And here, having filled up this place, because, okay, any one of 5 digits we can use. Only one digit will be used here, right? Now, having filled up the unit place, we are left with how many digits, okay? 4 digits, okay. here we can say any one of four digits we can use. Okay, any one of four digits. This place can be filled up by any one of four digits. Any one of four digits. So in how many ways we can fill up? Four ways. Okay, we can fill up this tens place in four ways. And now 1 2 digits gone, right? Now how many digits are left? Okay, now we have a three digits. Okay, right? Total, okay, five digits. One pack, okay, one we have used. Okay, one we have used here. Now we are left with, okay, having filled, okay, two places, we are left with how many digits? Okay, three digits. Okay, right? So here we can use, okay, for this, okay, how many choices? Any one of four. Okay, so here three digits we can use. Okay, any one of three digits. So there are three choices for 100 place, and here three ways. So we can say, okay, first operation can be we have performed in five ways independently in different, and second in four ways in different ways, and three in different ways. So total, okay, now, okay, total in how many ways, okay, total operations can be performed. So we can, okay, by using principle of basic principle of counting, we can write down now 3 times 4 times 5. Okay, 5 fours are 20, 20 is 60, and okay, 60 ways, okay, we can arrange these digits to make three-digit number in 60 ways. Well, in another way, okay, we can say we can make 63-digit number from the given digits 1, 2, 3, 4, 5. All right. Now I think it's clear. Now you are clear, absolutely clear about the fundamental principle of counting. Now you don't have any problem, right? Now, in which case we can use, okay, plus. So here I'm telling you, here is three-digit number. So if I say, okay, at least three-digit number, okay, at least three-digit number from, okay, from these digits. If I use, okay, this sentence, if I use at least three-digit number from 1 2 3 4 5, how many digits are there? 1 2 3 4 5, 5 digits. There are 5 digits. There are 5 digits. Now we want to make at least three-digit number. At least three-digit number means three-digit number we have to make, okay, and four-digit number and five-digit number, because we have maximum 5 digits, so we can make up to 5-digit number. So at least 3 digit means we have to make 3-digit number, we have to find out 4-digit numbers, and we have to find a number of ways in which 5-digit number we can make. All right, so meaning of at least mean this one, right? At least 3 digit means, okay, either 3-digit number or 4-digit number or 5-digit number from 1 2 3 4 5 6, because there are, okay, 5 digits. That's why we can go up to 5 digits number, right? uh, okay, now here, okay, we will find out 3-digit number, same, okay, fundamental principle of counting. Here 4-digit number same way, 5-digit number same way we can use, right? And then to find out the answer of at least three-digit number, then what you will do? We will do, okay, because, okay, I told you, okay, at least three-digit number of total number of ways in which we can make at least three-digit number from the given 5 digits is equal to three-digit number of ways in which three-digit number are formed, plus number of ways of in which, okay, 4 digits number, and plus 5 digit number, okay, right? Plus 5 digit number means, okay, number of ways in which, okay, 5 digit can be performed, okay. We'll, okay, number of ways, okay, number of ways plus something ways, this one, and plus something ways, and plus something ways we'll get, and that will give you the total number of ways in which we can make at least three-digit number from the given digit. Here we used, okay, addition principle, right? Because here independent, okay, there, right? Either 3 digit or 4 digit or a 5 digit is equal to a number of ways plus number of ways plus number of ways. All right. Now I think you are clear about the basic principle of counting. Let's move. Okay, now. Okay, now let's move into the main topic. Today's main topic, permutations, and then more main is your theorem, right? Very important theorem. I'll write down okay later. A very important theorem. Today, okay, permutation. Listen to me, everybody. Okay, literal meaning of permutation means arrangement. Simple. Okay. What do you mean by the permutation means? Arrangements. Okay, permutation means arrangement. All right. So here arrangement means order matters, right? So order of the object matters here. Like, see, okay, so let's see the definition of permutations. Permutation means different arrangements, okay? So, literal meaning arrangements, as I told you here. Permutation, your, let's see the definition. The different arrangements, permutation is different arrangement which can be made out of a given number of objects by taking some or all at a time are called the permutations, right? Just arrangements, okay? Or different arrangements, right? Taken some or all at a time. Here examples I've taken. For examples, all permutations, yeah, that is arrangements here, okay? All permutations and arrangements are made with the letters ABC. I have taken here 3 letters ABC by taking 2. Okay, this time, okay, taking 2 at a time are, these are the, okay, A, B, B, A, because as I told you in permutation order of the objects matter, right? Here A, B and B are not same, okay? A, B, B, A is different arrangement, right? A, B, B, A, A, C, C, A, B, C and C, B. These all arrangements are called permutations of 3 objects taken 2 at a time, right? Permutations of 3 objects taken 2 at a time. And okay, so I have taken your example, all permutations made with the letters ABC, same ABC, taking all, okay, now I am taking all, right? All at a time, okay, are ABC, ACB, BAC, BCA, CAB and CBA. These all are the different arrangements, right? These are the permutations, right? And now see, permutations of an objects taken are at a time is denoted by P of n comma or npr, okay? You can use, okay, either symbol to denote the permutations of an object taken are at a time, either this one or this one, it doesn't matter, any one you can use, right? And one more thing, see, listen to me, n is greater than equal to r here, right? N is greater than or equal to r, you can't have a less than n, okay, less than r, right? N is greater than or equal to r, okay, right? Okay, now see, using this symbol, now I can tell you here. So 3 letters here. How many letters? 3 letters by taking 2 at a time. Okay, these are permutations. Okay, we can represent a P of 3 comma 2 is equal 1, 2, 3, 4, 5, 6. So how many? 6 we got. Okay, by counting. Later we will find out the formula for this. So I'm going to find out. Okay. P of 3 comma 2 is equal to 6, okay, here by counting number of arrangements of 3 elements, 3 objects taken 2 at a time, or permutations, total number of permutations of 3 objects taken 2 at a time is equal to 6. Now here permutations made with the letters A, B, C taken all, okay. So okay, again taking all 3 comma 3. Here what do you mean by this one? Means permutations of 3 objects, yeah, 3 things taken all, means taken 3, taken all at a time is equal to, let's count how many arrangements are there. 1 this one, 2, 3, 4, 5, 6. Here also we have 6 arrangements. Alright. So this is your permutation. So once again, let me summarize. Okay, permutation. So permutation means, number 1, permutation means different arrangements. Alright, different arrangement. Permutations mean different arrangements, and in permutation, order of the objects matters. Alright. Okay, and permutations of n objects taken are at a time is represented by P of nr or npr. Okay, so I think now you are clear about the definition of permutation. What do you mean by the permutation? You can say immediately, oh, what is the permutation? Different arrangements are. Okay, so now you have no problem, right? Now let's move into the very important, one of the important theorems in permutation. Okay, so let's move into the theorems. Let's see the theorem. Very important theorem. What is the theorem? Total number of permutations of set of n objects taken are at a time is given by p of n comma r is equal to n into n minus 1 into n minus 2 into dot dot, yeah, into n minus r plus 1, or where n is greater than or equal to r, or p of n r is equal to n factorial. Factorial already we have discussed, right? Factorial in earlier video. We have discussed about the factorial. I have made, okay, if you don't know about that video, you can search and go through that factorial topic. N factorial upon n minus r factorial. Okay, now see, okay, here total number of permutations of set of n objects taken are. What is the meaning of this one? Here I have written, meaning of this one is total number of permutations of n objects taken are at a time is the same, yeah, or is equal to the number of, is the same as the number of different ways in which r places in a row can be filled with n different ways, with different objects, okay, in n different objects. So once again, the total number of permutations of n objects taken are at a time is equal to the numbers of ways in which our positions or our places, you can say, can be filled up with n objects. All right, or in a row, okay, one, you know, in a row, okay. Because in a circle there is a different arrangement, there is a different, okay, theorem for arrangements of the objects in a circle. Here that's why we have used here in a row. So important word here also, this important, in a row. Okay, so once again let me recap, let me, okay, recite this line. What is that line? The total number of permutations of n objects taken are at a time is equal to the, or is same as the number of different arrangements, right, in which r places can be filled up in a row by n objects. Okay, or you can read like this way: number of different ways in which r places or r positions, you can say, r places or r positions in a row can be filled with n different objects. So I have made, okay, boxes here. So I think you can't get, okay, these type of boxes in any work. I have made, okay. Okay, so this will give you a very clear, okay, idea how to prove this theorem. So see, okay, first place, how many, okay, in the beginning, how many objects are there? N objects, right? How many objects are there? N objects. For first places, okay, here we can choose any one, okay, any one of n objects we can take here, right? Any one of n objects we can use. So this means, okay, first place, okay, can be filled up in n ways, okay. In how many ways we can fill up? N ways, okay. There are n objects. It's clear that there are n objects. Any one can be used for first place. Hence, there are n ways, okay, right, to fill up the first positions, right? There is an, okay, and having filled up the first place, okay, when first place has been filled up with n ways, okay, by n ways, we are left with n minus objects. So we are left with, okay, we are, right, left with n minus 1 objects, means having filled up first places, right? First place, having filled up first place, because first place, any one of n objects we can take here any one object we can take. Okay, okay, so only one object will be used here. So having filled up the first place, we are left with n-1 objects, right? So here we can use, okay, any one of n-1 objects. Here any one of n-1 objects we can use. All right. Here I can write n-1 ways. If you can use, okay, any one of n-1 objects, this means there are n-1 ways, right? Similarly, having filled up first two, having filled up second, when second position has been filled, we are left with n-2 objects, n-2 objects, and because, okay, out of n, one is gone here, one is gone here, now n-2 left, right? Here we can use any one of n-2 objects, right? And any one of n-2 objects. And here you can write n-2 ways. What you can write down here? n-2 ways, right? Now let's see, okay, having filled up, okay, so on, okay, how many objects will be left for rth place, right? Having filled up, okay, r, here r-1, having filled up r-1 way, one place, then how many elements will be left, okay, for rth place? Let's see, let's check, okay. Okay, here I'm going to explain. First place, n ways, right? N object, okay, n ways, and second place here n objects, out of n objects, and here n-1, here n-1 object, and third place here n-2, here n out of any one of n-2 objects. Now let's see, okay, how many, okay, any one of how many, any one of, okay, objects we don't know. Okay, let's see. See, first position n object, all right. Second position n-1 objects, right? We are left with n-1 objects, right, for second places, and for third places n-2 objects are left, okay, right? See here, if second and here 1 means, okay, one less, okay, right? n-2 minus 1, one less, right? And here also we can, here if first n-1 minus 1, one left, see only, so n, right? Here third, so matching, okay, here n minus, because 2 is 1 less than 3, so 3 minus 1, yes, so n-1 means 2, okay, matching. All right, so similarly for this, what we can say, okay, here if r places, then n minus r minus 1, right? So is equal to n minus r plus 1 objects, right? So here having filled up r minus 1 places or a position, we are left with n minus r plus 1 objects, n minus r plus 1. Here I have told how we got, okay, n minus r plus 1 objects, right? Rth place, okay, so we can, any one of these objects we can use. So how many ways we have, okay, n minus r plus 1 ways we can write down, okay, right? We can, okay, fill up rth place in n minus r plus 1 ways. So very simple, okay. If you know, okay, how to fill up these boxes, then your theorem is over, and after that we have very easy process. All right, now see here, all things I have written in sentence. After this you can move here, same thing, whatever I have made, whatever I have explained here, all things are written here. It's clear that simple, all things whatever I have explained, okay, right? It's clear that there the first place can be filled up by any one of these n objects. So there are n ways of filling up the first place, n ways, and the having filled up the first place, we are left with n minus 1 objects. Now the second place can be filled up by any one of these n minus 1 objects. So there are n minus 1 ways of filling up. Alright. And the second, okay, the second filling of the second place. Similarly, now I've written okay here, similarly because we will continue the same process. Similarly, there are n minus 2 ways, okay, to fill up the third position and so on. Ultimately, to fill up the rth place, there are this minus this. Here I have explained okay how we got okay. N minus r minus 1 means is equal to n minus r plus 1 choices. Okay, now I think you are clear. Now I'm writing after that. Okay, so I'm going to erase all these things. Okay. um, so after this line here, by basic principle of counting, the total number of ways in which positions can be filled up by an objects is given by, okay, see, by basic principle of counting, because now we are going to use the basic principle of counting. Here we need okay basic principle of counting. That's why okay I have okay firstly explain basic principle of counting. The total number of ways in which our positions can be filled up by an object is given by already okay, right, is given by p of n comma r is equal to the product of, right, different product of ways, okay, product of different ways, okay. First, okay, see here n1 ways, where is okay, there are n ways, n times your second okay with n minus 1, and here n minus 2 ways we can, this is according to the basic principle of counting. We need to multiply the different ways, uh, and here n2 times n minus 2 ways, and dot dot times n minus r plus 1. Okay, the theorem is finished. Now by basic principle, the total number of ways in which our position can be filled up by an object is given by p of nr. Okay, so I here n comma r is equal to n times n minus 1 times n minus 2 times dot dot times n minus r plus 1. Now let's do something more here. Is equal to, let's try to convert into the factorial, right? So how to write down in factorial? Okay. Now I'm going to write here. Now let's convert into the factorial, same thing. Okay. Look at here, p of n comma r is equal to n minus 1 into n minus 2 into your dot 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 into, and n minus, or simply okay you can write down like this, dot 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 into n minus r plus 1. Now let's try to extend the products to up to 1. See here, if we have a 10, 7, let me tell you one factorial concept. 10, 9, 8. Now if you want to convert this this expression into factorial, we can write down like this with 10 times 9 times 8. Firstly, we have to know what is the factorial. Factorial n. Factorial n means continued product of first n natural numbers, right? Using the same that concept, we have to if we want to convert 10 factorial, then we need to write down the product of first 10 natural numbers. 10 times 9 times 8, 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, now because here 10 times up to 8, here 10, 9, 8, up to 8 we have numbers, but these numbers are not there. Product of these numbers are not given there. These all are here extra. Let's cancel by multiplying but in denominator by, so you can say by dividing. You can cancel these numbers by dividing by the same numbers. 5, 4, 3, 2, 1. Product of the same numbers times 1. 7, 6, 5. 1, 2, 3, 4, 5, 6, 7. All right. And now, according to the n factorial definition, we can write down here 10 factorial over 7 factorial. The same concept we have to use here, right? So n factorial, because is here this expression, expression is started with n, so definitely it will come in n factorial. If you want to write down the n factorial, we need to write down the product of first n natural numbers. Let's write down, let's complete product of first n natural number. N minus r plus 1 less n minus r 1, 1, you have to decrease, n minus r minus 1. So and here you write down n minus r minus 2 and so on. Finally 3, 2, 1, right? If you have any confusion, you can see the tutorial video of factorial. And now n minus r, because these all are extra in product, let's cancel this by dividing by the same product of same numbers. N minus r minus 1, n minus r minus 2 dot dot 3, 2, 1. Now or p of n comma r is equal to here. So if you see very carefully, you will find continued product of first n natural number, and here continued product of first n minus r natural numbers. So we can write down n factorial upon, here we can write down n minus r factorial. So this is the theorem, we can say now. Hence yes, so so the total number of permutations of an objects taken are at time is given by p of n-r or n p-r. You will write down like this, n factorial upon n minus r factorial. This is the theorem, hence the proof. One of the very important theorems, right? Note down one. So here, if we take an r at all time, so taken all means, so total number of permutations of an objects taken all at a time is given by n factorial upon n minus n factorial is equal to n factorial upon 0 factorial. As we know, the 0 factorial is 1. So n factorial upon 1 is equal to n factorial. You can use this. If you are taking all at a time, then you can say n factorial. Then no need to use this formula. No, you can just reduce one step, right? At least you can say directly. You can say n factorial. If you are making arrangements of 7 letters taken all at a time, then you can say 7 factorial. Arrangements of 6 letters. Okay, taken all at a time, 6 factorial. Okay, so directly n factorial you can use formula. All right. Now I think you understood this theorem fully. If you have still any problem, please don't hesitate to ask question, or you can write down in comment box. Definitely I'll give the answers of your question. Okay, and we will discuss the question based on this theorem in my next video. Thank you for watching. Bye bye.